Hi everyone! I hope you're all doing well. Today we're going to start chapter 9, which is all about acids, bases, and salts. So we're going to start with just acids and bases, and then later on we'll talk about salts. Alright, so let's start with a basic definition of acids and bases. No pun intended. So one of the definitions for acids and bases is called the Arrhenius definition. So an Arrhenius acid is any substance that provides hydrogen ions, H+, when dissolved in water. And Arrhenius was a scientist, I believe in the early 1900s, and this definition is more specific to certain types of acids and bases. Later on, we'll see a broader definition of acids and bases. So, as an example of an Arrhenius acid, let's look at HNO3. So, HNO3, when dissolved in water, ionizes. So, we end up with H+, and the nitrate ion, NO3-. So HNO3 is actually a covalent molecule. So it's not an ionic compound, but when it dissolves in water, it can produce ions, which is kind of cool. So an Arrhenius base is any substance that provides hydroxide ions, or OH-, when dissolved in water. So one example is potassium hydroxide, KOH, and this is an ionic compound because it has a metal bonded to a polyatomic ion. So we do know that potassium is always soluble in water. So when we add KOH to water, it dissociates into potassium ions and hydroxide ions. So you'll notice I used two different terms there. Up above with our acid example, because HNO3 is a covalent molecule, we say that it ionizes in solution. But if we start with an ionic compound like KOH, that just dissociates because it's already ionic. So it's just separating in water. Now, that's just a small side note, but I might say ionizes or dissociates, and that's why I'm using those two different terms. Okay, so let's look at a different definition for acids and bases. So this definition is a little broader. So this is called the Bronsted theory, although sometimes it's in combination with another scientist, Lowry, so it's called the Bronsted-Lowry theory sometimes. So a Bronsted acid is any hydrogen-containing substance that is capable of donating a proton or hydrogen ion to another substance. All right, so we're using the term proton here because remember that hydrogen has one electron. It also has one proton. And the proton is what gives hydrogen its mass. But if it loses that one electron to become a hydrogen ion, all that's left in that atom is one proton. So that's why we can call it a proton. So sometimes you'll hear hydrogen ions referred to as protons. All right, and then a Bronsted base is any substance capable of accepting a proton from another substance. Okay, so the Bronsted acid definition is really similar to the Arrhenius definition of an acid, but the Bronsted base definition is a little bit different here. So remember on the last slide we said that an Arrhenius base is any substance that provides hydroxide ions in water. But the Bronsted definition says that a base is any substance capable of accepting a proton from another substance, so a hydrogen ion. Now, this is a broader definition because some bases, they might produce hydroxide ions in solution, but it's not obvious that it does. This Bronsted base definition just kind of allows for a broader group of bases. Okay, so down below we have an example of a Bronsted acid reacting with a Bronsted base. All right, so we've got HNO2 reacting with water. And then you'll notice that our products are the hydronium ion, H3O+, and NO2-. So NO2- is our nitrite polyatomic ion. And if we look at the reactants versus the products, we can see that HNO2 lost a hydrogen. So that must be our acid because it gave up a hydrogen ion. And then the water molecule turned into H3O+. So it actually gained a hydrogen or accepted a proton from HNO2. So that would be our base. So in this reaction, HNO2 behaves as a Bronsted acid by donating a proton or hydrogen ion to the water molecule. The water molecule behaves as a Bronsted base by accepting the proton. And then we end up with our two products, H3O+ and NO2-. All right, so acids and bases can be found all over the place. We'll talk more about properties of acids and bases later. But some examples would be, for instance, if you use limes or lemons. Limes and lemons contain citric acid. And if you've ever tasted or bit into a lime or a lemon, it's pretty sour, right? So that sourness comes from the acid. Another example is vitamin C. Vitamin C is actually an acid. It's called ascorbic acid, and vitamin C is really important for the health of our teeth and our gums, etc. And then examples of bases would be soap. Some soaps are basic. A lot of cleaning products are basic, like laundry detergent, or if you use bleach to clean things, which I've been using a lot of lately, just with the pandemic. But if you've ever touched some of your cleaning products by accident, you might have noticed they felt kind of slippery or soapy. So bases tend to have that kind of slippery feel. So we come across acids and bases all the time. All right, so we just saw how an acid and a base can react with each other, but let's talk a little bit more about the products. So we saw that HNO2 lost a proton or donated a proton and became NO2-. So we just said that HNO2 is an acid, but when it turns into NO2-, it becomes basic. So we would call the product a conjugate base. Now, the reason that it's a base is because it could now accept a hydrogen ion, because we could go in the reverse direction. We have a double arrow here. So NO2- could grab onto a hydrogen ion and reform HNO2. So we call that a conjugate base. Now, similarly, let me use a different color here. So H2O accepted a hydrogen ion, so that was our base, and then it became H3O plus, and we would call that the conjugate acid. Oops, there we go. So H3O plus can act as an acid because it could give one of its hydrogens to NO2 minus and reform the water molecule. So if we went in the reverse direction, H3O plus would act as an acid and NO2 minus would act as a base. Okay, so now we can see that there are pairs of acids and bases. We have our conjugate acid-base pairs. So our first pair is the Bronsted acid, HNO2, and its conjugate base, NO2 minus. And then the second pair is between water and its conjugate acid, H3O plus, also known as the hydronium ion. Okay. All right, so let's talk a little bit more about acids because there are a lot of different acids out there. So one type of acid is called a binary acid. So binary acids like hydrochloric acid, HCl, those are formed by dissolving the gas in water. So if we have gaseous HCl, we can put that in water and that will form an acid. Now the term binary is just referencing the fact that there are only two atoms in the acid. All right. So, or rather two types of atoms, I should say, because down below we can see that HCl, HI, HBr, and H2S are all binary acids. And H2S does have a second hydrogen, but we only have two types of elements in that compound, so it is a binary acid. Now the other type of acid contains polyatomic ions bonded to one or more hydrogens, and we'll talk more about those later. So let's learn how to name binary acids. All right, so let's use the example of HCl, because we already know the name is hydrochloric acid. So rule 1, we start with the prefix hydro, and then rule 2, we drop the suffix IDE and replace it with the suffix ic. So for instance, previously we might have named this hydrogen chloride, right? Because it's a covalent molecule. But when we're naming it as an acid, we're going to start with hydro and then start with the base name of chlorine, and then we're going to drop that IDE and replace it with ic, and then we're going to add the word acid to the end. So that's where we get the name hydrochloric acid. Now, there's some other examples like hydroiodic acid, that would be HI. Another example is HBr. We call this hydrobromic acid. Let's see, what's another example? HF is hydrofluoric acid. This is actually a pretty dangerous acid. It's a weak acid, which is interesting, but if it touches our skin, fluorine is small enough that it can penetrate our skin and it can cause damage to our organs and actually eat away at our cells. So if you've seen Breaking Bad, there was a scene where they used hydrofluoric acid to dissolve a body, but yeah, so you want to avoid hydrofluoric acid. All right. And then let's see, H2S was another one that we saw. So we would name this hydrosulfuric acid. So the hydrosulfuric acid is a little different because we're using the full name of sulfur. We're not dropping that last part and adding ic acid. So that one is a little bit different. Okay. So I mentioned that there are other acids that contain polyatomic ions. These are referred to as oxyacids because they all have oxygen in them. So notice, for instance, the examples, all of them have oxygen. So they are called oxyacids. All right, but you'll also notice they all contain a polyatomic ion that's bonded to hydrogens. So this is one reason to memorize the polyatomic ion names, because we're going to use those when we name these acids. So if you need to go back and review those flashcards I posted, definitely do that. All right, so how do we name these oxyacids? Rule 1, all hydrogen atoms that are written as the first part of the formula of the acid are removed in solution. So for instance, we saw that HNO3 will ionize in water to produce H plus and NO3 minus. All right, so the polyatomic ion that remains after all of the hydrogen ions are removed is just named as usual. So for instance, we said that this ion here is nitrate. All right, so if we're going to name that acid, we can see that the ending of that name is ATE. So rule 3, when the remaining polyatomic ion has a name ending in the suffix ATE, the suffix is replaced by the suffix ic, and the word acid is added. So HNO3 would be named nitric acid. So we dropped the ATE from before and replaced it with ic acid. Now notice we don't have hydro in front of this name. That's only for binary acids. And again, binary acids have two elements, but no more than just two different types of elements. Whereas oxyacids have this polyatomic ion that contains oxygens. So we use a different method to name them so that we can keep them separate from the binary acids. All right, now there's a couple more rules for naming these oxyacids. All right, so let's say that instead of HNO3, we're looking at HNO2. So that will ionize in water to give H plus and NO2 minus. And that polyatomic ion is nitrite. So the ending has changed. So when the remaining polyatomic ion has a name ending in the suffix ITE, that suffix is replaced by the suffix OUS, or us, and then the word acid is added. So HNO2, its name would be nitrous acid. So we replace the ITE with us acid. Okay, and then you'll notice a couple of acids up above that have sulfur and phosphorus in them. So how do we name those? Now, if the polyatomic ion contains sulfur or phosphorus, the stems sulf or phosp that remain when the suffixes ate or ite are replaced are expanded to sulfur and phosphor before the ic or us suffixes are added. Okay, so let's look at those examples. So H2SO4. So the polyatomic ion is SO4, which would have a charge of 2 minus, and its name is sulfate. So that's the sulfate ion. So the acid would then be named sulfuric acid. So we're just expanding the sulf to sulfur. And that's similar to what we saw before with H2S, where it was hydrosulfuric acid. So we kept the full name of sulfur. And then for an acid that contains phosphorus, like H3PO4, the polyatomic ion is phosphate, and the acid name is phosphoric acid. So we're kind of including that extra syllable there. So phos becomes phosphor. All right. So naming acids can be a little bit tricky, but as long as you know the difference between a binary acid and an oxyacid, and as long as you know the names of the polyatomic ions, you'll be good to go. Okay, so one more thing before we go today. Water is an interesting molecule because water can act as an acid or a base. So we would call it an amphoteric substance because it can be both an acid or a base. So let's say we have a glass of just pure water. Now, pure water doesn't just contain water molecules. Water can actually react with itself to produce a conjugate acid and a conjugate base. So we could just arbitrarily assign down below, let's say the first water molecule is an acid and the second one is a base. So remember that acids donate a hydrogen ion. And then bases accept hydrogen ions, at least according to our Bronsted theory. So if one water molecule gives up a hydrogen, it's going to become OH minus. And then if the other water molecule accepts a hydrogen ion, it becomes H3O plus, our hydronium ion. So H3O plus, if we go in the reverse direction, could act as an acid and give up that hydrogen ion. So that would be our conjugate acid. And then OH minus would be the conjugate base because it could accept a hydrogen ion. So what's interesting here is that a very specific amount of hydronium ions and hydroxide ions are produced. So if we have 1 liter of pure water, 1 times 10 to the negative 7th moles of water molecules will behave as Bronsted acids and donate protons to another 1 times 10 to the negative 7th moles of water molecules, which act as Bronsted bases. So when water interacts with itself, we produce 1 times 10 to the negative 7th moles per liter of H3O plus, and we also produce 1 times 10 to the negative 7th moles per liter of OH minus. Now this is a very, very small amount, so that's why water doesn't taste particularly acidic or particularly basic. But additionally, we have equal amounts of our conjugate acid and conjugate base, so they kind of cancel each other. So instead, we describe water as neutral. So because we have equal amounts of hydronium ions and hydroxide ions, or conjugate acid and conjugate base, again, any properties that they might have as acids or bases, they cancel each other out. So overall, water is neutral. Now, again, you'll notice that we have double arrows here. So this reaction could go back and forth, which means that it eventually will reach equilibrium. And remember in chapter 8, we saw that we can write an equilibrium expression for a reversible reaction. So down below, we have the equilibrium expression for water. So remember, K is the equilibrium constant. And remember that to determine K, we take the concentration of the products and then divide it by the concentration of the reactants. So in the numerator, we have the concentration of hydronium ions multiplied by the concentration of hydroxide ions, and then we divide that by the concentration of water. But we do have 2 moles of water in our reactants, so we're just going to square the concentration of water. So what this leads to is something called the ion product of water. So the reaction that we saw in the last slide is called the self-ionization of water, which produces, again, hydronium ions and hydroxide ions. And we just saw that we can write the equilibrium expression for that reaction. Now, in the denominator, we have the concentration of water squared. However, only a small amount of water reacts to establish equilibrium. So that means that the concentration of water remains essentially constant. So we can actually ignore the denominator, and this is true for any equilibrium expression. So we typically don't include pure solids or pure liquids in our equilibrium expression because their concentrations don't change very much during a reaction. So don't include pure liquids or solids in, in K. All right. Now, we can include gases and aqueous solutions. That's totally fine. So H3O plus and OH are both considered aqueous because they're dissolved in water. So we can include those in our expression. So if we rearrange our expression, so let's move H2O over to the left-hand side and we'll multiply it by K. We're going to replace this part of our equation with something called Kw. So because the concentration of water is essentially constant, the product of K multiplied by the square of the water concentration is equal to another constant, designated as Kw. So Kw is called the ion product of water. So Kw, or the ion product of water, is equal to the concentration of hydronium ions multiplied by the concentration of hydroxide ions. Now remember earlier we said that those concentrations were 1 times 10 to the negative 7th moles per liter for both. So if we multiply those together, we can get the ion product of water value. So down below, we're plugging in 1 times 10 to the negative 7th for both of those concentrations, and we'll just square it because both are the same. And what we get is this value of 1 times 10 to the negative 14th. So this value is going to become very important and very useful later on. But I think we're going to stop there for now, and next time we'll talk about how we can use this ion product of water to determine how acidic or how basic a solution is. So I will see you in the next video.